In this file, you're going to see some informal proofs of circle theorems using what we already know, our prior knowledge in geometry. Okay, so the first theorem that we want to prove is that an angle in a semicircle is a right angle. So you start off, you have a triangle. You know that triangles are behind just about everything. So they have this triangle that's inscribed in a semicircle, right? The technique is that you would split the triangle up. So now you make this extra radius, and in a circle all radii are congruent. So we name them R, R, and R. So that means that I have two isosceles triangles. So I name the base angles in the left triangle. I name those A and A. And then I name the base angles in the right triangle B and B. Then I take away this segment in the middle. Let me erase it. So what do I have? I have that A, right, plus A plus B is 180. So again, that is A plus B is 180. Or 2A plus 2B is 180. If I divide everything by 2, I get A plus B is 90, which means that this angle over here, inscribed in the semicircle, since A and B add to 90, that angle must be a right angle. So let's continue on. In this proof, we're going to prove that an angle inscribed in the same arc as a central angle is either half its measure, or we could say the central angle is twice its measure. So we start off, we have this angle B inscribed in this arc, right? Then we have this angle A that is the central angle of the same intercepted arc. So this intercepted arc is the same for both B and A. So you start off with the same technique. You're going to make this extra radius. And then we have in the left triangle, we have W and W as the base angles. In the right triangle, we have Y and Y. And then you can just pick two other angles. It doesn't matter what you call them, X and Z. So in the left triangle, you have 2W plus X equals 180. In the right triangle, you have 2Y plus Z equals 180. So there's many techniques to solving this system, but one technique is if you solve for X over here, 180 minus 2W, and then you solve for Z over here, we know that angles around a point have to add up to 360. So we have this angle A in the picture. I'm putting it back in. So therefore, we have A plus X plus Z equals 360. And we can take 180 minus 2W and sub that in for X. 180 minus 2Y, sub that in for Z into this equation. Now I'm just going to combine like terms. So 180 is 360, minus 2w minus 2y plus a is 360. So as we know, okay, the 180 minus 2y is equal to z. So what we have here is that a minus 2w minus 2y is 0, because you can cancel out these 360s. That's an a. That's just a typo. So that means that a equals 2w plus 2y, right? Just bring those over to the right, which means that a is twice w plus y. But we already know that w plus y is b. So then we can conclude that the central angle is twice the inscribed angle. QED, by the way, just means, in case you're curious, that's really sloppy, just means quod est demonstratum. All right, which means that which we set out to prove, we have thus proven. Let's move on. So angles in the same segment. What we're talking about here are two angles that are inscribed to the same arc. So you can see I have this angle A, which is inscribed to this arc. Then I have this angle B, which is inscribed to this arc. So we're going to set out to prove that those two angles are congruent. So we start off, we make a central angle, because you can use what you've already proven in previous proofs to do the next proof. So here I have this central angle C that's also inscribed in that same arc as A and B, right? So we know that angle C, all right, is twice the measure of angle A, and we know that angle C is also twice the measure of angle B. So it would stand to reason if C is twice A and C is twice B, well then A and B must be congruent. Okay, but this should be, but angle C must also be twice. All right, let's take a look at the next proof. So that proves that angles inscribed in the same arc are congruent. Opposite angles in a cyclic quadrilateral. So I'm going to draw a central angle for angle B. If I draw that, I know that this angle is 2B. So this should be 2B. Then if I draw a central angle for A, so remember when you're drawing a central angle, and I want to deal with A here, I take these two vertices, it has to go through the center. So here's the central angle for A. This would be 2A. So what I have is 2A plus 2B equals 360. And therefore, if I divide everything by 2, I get that A and B must add to 180. So that proves the theorem correct. All right, let's take a look at this alternate segment theorem. First, let me show you what we're going to prove. So I'm not crazy about the symbols they use here, so I'm going to just use my own. So I have A, right? You can see that A is inscribed in this arc, right? So now, what I'm going to do, I drew this diameter in red. Okay, that is a diameter. And I'm going to make use of the third proof. So I'm going to now draw this. If I draw that, do you see that this is a right angle? Because it's inscribed in a semicircle, and we've already proven that. We also know that this is also angle A. So both of those are A because they're inscribed in the same arc, this arc here. Now I'm going to call this angle angle C. And if this is 90 degrees, what would that mean about this angle A and this angle C? They would be complementary, correct? So I would have A plus C equals 90 degrees. Now, if I take a look at this angle here, let me use a different color. So let's look at this angle here. Okay, so I'm going to call that A2. This angle, I'll call that A2. So I guess I'll go back and call this A1. Now, if you look at that A2, okay, we know that if you take angle C and you take A2, let's put those together for a second. So if you look at this, A2 and angle C, how do we know that those are complementary? Okay, because we have a theorem that tells us that when you have a tangent is perpendicular to the radius at the point of tangency. So that means that A2 plus C is 90 degrees. Now, if I subtract the one equation from the other, I get A1 minus A2 equals 0. Therefore, A1 equals A2. So what this proves is that if you have an angle that is inscribed in an arc, it's going to have the same measure as an angle formed by a tangent, okay, and this chord. So that angle formed by the tangent and chord is literally equal to the angle that's inscribed in this arc. So whether you have a chord tangent or you have two chords making an inscribed angle. So an angle formed by a chord tangent inscribed to the same arc as an inscribed angle will have equal measure. Hope this video has helped you to see that these facts that we've learned actually make sense.